Hello everyone. Thanks to everyone for watching this video. My name is Qi. I'm an architect and engineer. Today's video is titled Flow over Immersed Body, and it is going to provide you a broad overview of the external floor and also the jack and the lift. I'm going to give you an overview of what I'm covering today's video. First at all, we will have a look at some fundamentals of the external floor, then move on to the aerodynamic jack and lift, then wrap up with conclusions. In this video, we consider the aspects of the flow over bodies that are immersed in a fluid. Examples include the flow of air around airplanes, automobiles, and falling snowflakes, or the flow of water around submarines and fish. In these situations, the object is completely surrounded by the fluid, and the flows are termed external flows. A body immersed in moving fluid experiences a resultant force due to the interaction between the body and the fluid surrounding it. In some instances, the fluid far from the body is stationary and the body moves through the fluid with velocity u, the upstream velocity. There is a uniform, constant velocity fluid flowing past the object. In actual situations, this is often not true. Usually, the unsteadiness and non-uniformity are of minor importance. When any body moves through a fluid, an interaction between the body and the fluid occurs. This effect can be given in terms of the forces at the fluid-body interface. These forces can be described in terms of the stresses, or shear stresses on the body, tau W, due to viscous effects, and normal stresses due to the pressure, P. Typical shear stress and pressure distributions are shown in Figure A and B. Both tau W and P vary in magnitude and direction along the surface. It is often useful to know the detailed distribution of shear stress and pressure over the surface of the body, although such information is difficult to obtain. Many times, however, only the integrated or resultant effects of these distributions are needed. The resultant force in the direction of the upstream velocity is termed the jack, Fd, and the resultant force normal to the upstream velocity is termed the lift, Fl, as is indicated in Figure C. The resultant of the shear stress and pressure distributions can be obtained by integrating the effect of these two quantities on the body surface, as is indicated in this figure. The x and y components of the fluid force on the small area element dA are expressed here. Thus, the net x and y components of the force on the object are given by these equations. Of course, to carry out the integrations and determine the lift and the jack, we must know the body shape. For example, theta as a function of location along the body, and the distribution of tau W and P along the surface. These distributions are often extremely difficult to obtain, either experimentally or theoretically. The pressure distribution can be obtained experimentally by use of a series of static pressure taps along the body surface. Although the two equations are valid for any body, the difficulty in their use lies in obtaining the appropriate shear stress and pressure distributions on the body surface. Considerable effort has gone into determining these quantities, but because of the various complexities involved, such information is available only for certain simple situations. Without detailed information concerning the shear stress and pressure distributions on a body, the two equations cannot be used. The widely used alternative is to define dimensionless lift and jack coefficients and determine their approximate values by means of either a simplified analysis, some numerical technique, or an appropriate experiment. The lift coefficient, Cl, and the jack coefficient, Cd, are defined as these equations, where A is a characteristic area of the object. Typically, A is taken to be frontal area, the projected area seen by a person looking toward the object from a direction parallel to the upstream velocity, u, as indicated by this figure. It would be the area of the shadow of the object projected onto a screen, normal to the upstream velocity, as formed by a light shining along the upstream flow. In other situations, A is taken to be the planform area, the projected area seen by an observer looking toward the object from a direction normal to the upstream velocity. Obviously, which characteristic area is used in the definition of the lift and the drag coefficients must be clearly stated. Next, we will introduce the aerodynamic lift and the drag. First, it is drag. The component of drag caused by the shear stresses is called friction drag, and the component caused by the pressure stresses is called pressure drag or form drag. Pressure drag is most significant for blunt bodies like this sphere. It is essentially caused by a difference in pressure between the front and the rear of an object. Pressure drag increases significantly if flow separation occurs, which is when the fluid boundary layer detaches from the body, creating a wake of recirculating flow. This creates an area of low pressure behind the body, called the separation region. That results in a large drag force. If you are trying to reduce drag forces, you will want to minimize flow separation at all costs. Flow separation can also cause vortex shedding, which can generate unwanted vibrations and instability. To understand why flow separation occurs, let's look at flow on the upper surface of the sphere. As the fluid passes over the surface of the sphere, it is initially accelerating, and so pressure is decreasing in the direction of the flow. This is called a favorable pressure gradient. Beyond a certain point, the flow then begins to decelerate, and so pressure in the flow direction is increasing. This increase in pressure is called the adverse pressure gradient, and it has a significant effect on the flow close to the wall. If the pressure increase is large enough, the flow will reverse direction, and since it cannot travel backwards because of the oncoming fluid, it detaches from the surface, resulting in flow separation. For very streamlined bodies, like this airfoil, at a shallow angle of attack, pressure drag is small because flow separation is significantly delayed, or doesn't occur at all. For bodies like this, it is the wall shear stresses which contribute most to the total drag force. The drag component caused by these stresses is called friction drag. Friction drag increases with the viscosity of the fluid, and is most significant for bodies which have a large surface area aligned with the direction of flow. We saw earlier that turbulence delays flow separation, which reduces the pressure drag. But for friction drag, it has the opposite effect. Laminar and turbulence boundary layers have very different velocity profiles. The velocity gradient at the wall is deeper in turbulent boundary layers than in laminar ones, and so turbulence produces larger shear stresses. So, to reduce friction drag, you want to delay the transition to the turbulent regime and maintain laminar flow for the largest possible distance around the object. Now we will use an example to illustrate the drag coefficient. A viscous, incompressible fluid flow past the circular cylinder shown in Figure A. According to a more advanced theory of boundary layer flow, the boundary layer remains attached to the cylinder up to the separation location at theta approximately equal to 108.8 degrees, with the dimensionless wall shear stress as is indicated Figure B. The shear stress on the cylinder in the wake region from 108.8 to 180 degrees is negligible. The friction drag can be determined as this equation, where B is the length of the cylinder. Note that theta is in radians, not degrees, to ensure the proper dimensions of dA equal to 2 times the half of d times b times d theta. Thus, we obtain this equation. This can be put into dimensionless form by using the dimensionless shear stress parameter f theta, given in figure B, and we can derive this equation. The function f theta times sin theta, obtained from figure B, is plotted in figure C. The necessary integration to obtain CDF can be done by an approximate numerical technique, or by an approximate graphical method to determine the area under the given curve, so that we obtain this result of CDF. Now we consider the pressure friction. The pressure coefficient on the surface of the cylinder, as determined from experimental measurements, is as indicated in figure B. The pressure jack coefficient can be determined as this equation. To obtain CdP, we must integrate the Cp times cosine theta function from theta equal to 0 to pi radians. Again, this can be done by some numerical integration scheme or by determining the area under the curve shown in figure C. The result is CdP equal to 1.17. The net drag on the cylinder is the sum of friction and pressure drag. Thus, we obtain the drag coefficient. This result is compared with the standard experimental value in figure D. The agreement is very good over a wide range of Reynolds numbers. It is of interest to compare the friction drag to the total drag on the cylinder. That is this equation. For Re equal to 10 power 3, 10 power 4, and 10 power 5, this ratio is 0.138, 0.0483, and 0.0158 respectively. Most of the drag on the blunt cylinder is pressure drag, a result of the boundary layer separation. Now, let's look at how the drag coefficient varies for a few different two-dimensional shapes. For a flat plate oriented at 90 degrees to the floor, the drag coefficient doesn't vary significantly with Reynolds number, because floor separation will always occur at the edge of the plate, and so, although it is a blunt body, it isn't affected by whether flow is laminar or turbulent. For blunt shapes like this disc, we see a large decrease in the drag coefficient at the transition between laminar and the turbulent flow, because flow separation is delayed when the boundary becomes turbulent, reducing the drag force. And for streamlined bodies, the drag coefficient reduces gradually as Reynolds number increases, since viscous forces are less significant at higher Reynolds numbers, but the drag coefficient begins to increase after the transition to turbulent flow, because as we saw earlier, a turbulent boundary layer produces larger shear stresses. Now we have introduced the drag. Next, we will introduce the lift. We know that lift is caused by the pressure distribution around the airfoil. But where does the pressure distribution come from? The answer to this question is complex, and there is much debate about the best way to explain it in a concise way. In this video, we will use Bernoulli's principle. Bernoulli's principle explanations focus on the velocity of the fluid. If we look at how fluid flows around the airfoil, we can see that close to the leading edge, there is a point where the fluid velocity is reduced to 0. This is called the stagnation point. Outside of the same boundary layer surrounding the airfoil, the fluid flowing above the stagnation point over the top surface of the airfoil travels faster than the fluid traveling over the bottom surface, as we can see from these particles. Bernoulli's principle tells us that when the velocity of a fluid increases, its pressure must be reduced, which is just a statement of the conservation of energy. This means that the increase in velocity above the airfoil creates an area of lower pressure, and the reduction in velocity below it creates an area of higher pressure, and this pressure difference creates the lift force. But then we need to explain what causes the difference in velocity. One explanation is that the geometry of an airfoil causes the flow to be pinched together above the airfoil, but not below it. Because of the conservation of mass, this results in increased velocity above the airfoil. A more complete but less intuitive explanation for the difference in velocity is based on the concept of circulation. The flow around an airfoil can be thought of as the superposition of idealized uniform rotational flow and circulatory flow. Without circulation, the flow around the airfoil would look like this. This is clearly non-physical, since the fluid cannot turn such a sharp corner at the trailing edge, and so the airfoil must be generating some circulation. If we impose a condition that says that the flow above the below the airfoil must be parallel when leaving the traveling edge, we can calculate the exact amount of circulation that must be generated by the airfoil to do this. This is called the Coulter condition. Circulation has the effect of accelerating the flow above the airfoil and delaying the flow below it, which gives us the explanation we need so that we can apply Bernoulli's principle. If we want to improve the lift force of this kind of airfoil, we can easily imagine, for example, that increasing the camber of an airfoil will allow it to deflect a larger amount of fluid, and so will increase the lift force. The same is true for the angle of attack. Increasing the angle of attack deflects more fluid and increases lift. However, there are limits to this logic. Once the angle of attack reaches a certain critical value, we can observe a sudden decrease in the lift force. For this airfoil, it occurs at around 16 degrees. At this angle of attack, the boundary layer is no longer able to remain attached to the airfoil, and it detaches from the surface, creating a wake behind it, which affects the pressure distribution around the airfoil, significantly reducing lift and increasing drag. The sudden reduction in lift is called, and it can be very dangerous for aircraft. Different airfoil shapes can have drastically different lift characteristics. This airfoil is cambered. If an airfoil is symmetrical and so has zero camber, the lift force will be zero for zero angle of attack. Modern aircraft wings are equipped with flats and slats which allow the shape of the airfoil to be adjusted and optimized for the different phases of flight. During takeoff, for example, you want high lift. Extending the flats increases the camber of the wing, which increases lift, and so flats are extended during takeoff. But the extra lift comes at the expense of increased drag, and so the flaps are retracted when cruising. Since high lift is no longer needed, and the drag should be minimized to improve fuel consumption. From conclusions, what we learned: the drag, which contains portions due to friction viscous effects and pressure effects, is written in terms of the dimensionless drag coefficient. It is shown how the drag coefficient is a function of shape, with objects ranging from very blunt to very streamlined. The lift is written in terms of the dimensionless lift coefficient, which is strongly dependent on the shape of the object. Variation of the lift coefficient with shape is illustrated by the variation of an airfoil's lift coefficient with angle of attack. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,